about something else completely different from last week's talk, which was about nonlinear construction. So instead, I will give my perspective where we are on the theoretical analysis of power spectrum of galactic structure in redshift space for galaxies. There are a couple of challenges that one needs to address when one wants to analyze the two-point function from galaxies. One is when we need to model the two-point function itself. I'll talk about an approach that we recently posted by Han et al., which goes to much higher K than what previous analyses have done. Then I'll talk about one way to remove some angular systematics. This was described in a couple of papers, et al. And Han et al. And finally, I'll talk about the covariance matrix challenges. I'll talk a little bit about the dark matter, and then also about the galaxies. Okay, so this is my collaborators on these papers. So let me start with the perturbation theory approach to modeling the power spectrum. The basic idea of perturbation theory, well, we try to use perturbation theory to model things. We want to go to as small scales as we can, and we want to be as general as possible so that we account for all possible nuisances. Okay, so the basic picture is the further we go to smaller scales, the more information there is, because now mode scales as k cubed. But the modes become nonlinear. And that means first of all, they're correlated. I'll talk about the covariance matrix challenge later. And second, the nonlinearities are not necessarily perturbative and not necessarily even predictable. Okay, so some of it can be modeled by perturbation theory and biasing. So this has, in our approach, we call this distribution function approach, has been described by these papers, Seljak et al. And Kimura et al. Papers. There's always more information on small scales, which is not perturbative, and often is hopelessly corrupted by nonlinear effects. So we need to parameterize our ignorance. That's one way to think about this, but we need to parameterize it in a way which is physically, which obeys all the symmetries, and is physically allowed. For example, we need to conserve mass and momentum during this process. We cannot just make things up such that mass and momentum is not conserved. This then leads to certain terms. This leads then to a very specific form of these terms, which obey all the symmetries. For example, at low k, all of these terms show up as k squared p linear, plus zero lag terms, which, depending on what we're looking at, can be either k to the 0 or k to the 4. And then all the physics means that these parameters that come in front of these terms have to be sort of more physically motivated. For example, by far the largest effect, nonlinear effect, is what we call fingers of God, the velocity dispersions inside of satellites into the clusters. And this one, we have some idea how big it is because it has something to do with the virial velocities of the clusters. Okay, so in recent years, the work has been the Halo model plus biasing plus perturbation theory. That's what we have done here. We have a new paper that combines this perturbation theory approach with a whole bunch of nuisance parameters. I won't go into details. Probably you've heard some talks about the perturbation theory aspects already. I just want to emphasize that we add basically the so-called Halo occupation distribution parameters in some form. For example, we add satellites, which we parameterize with cell fraction. We have to parameterize their mass, which means that their velocity dispersion is given by the mass. We have so-called one Halo term, which has to do with basically how many satellite central pairs we have and how many satellite pairs we have, and so on and so forth. So there's quite a long list of parameters that we need to introduce. But we claimed all of these are physical parameters that have to be there. Okay, and so there's no way of avoiding not to have these parameters. Some of these may not matter. That will show up when we marginalize over them. The maybe layers don't go up, but nevertheless they have to be there, at least in principle. Okay, so in terms of modeling, we have achieved about the factor of 2 improvement in terms of scale relative to previous work. Previously, people have usually stopped at either k.15 or 0.2. Here I'm showing in a monopole, quadrupole, and hexadecapole our model. These are residuals relative to the errors. You see that they're all around scattered around 1 sigma. I mean, the distribution is good. You should notice that the errors go up as we go to higher and higher multiples. For example, the errors on the quadrupole are about square root of 5, and larger than the errors on the monopole. There's no obvious residual. The precision is certainly within 1%, and so we think we have a good model. Sorry? This is redshift. This is redshift. No, this is full box. This is redshift 5.
You don't have any 2 signal points.
Sorry?
Doesn't seem like you have any.
There's one here. There's one here. Yeah, a couple of them. Yeah, right at the edge here.
The dash lines are 2 sigma?
Dash lines 2 sigma. These are
I see. Oh, sorry.
Okay, so now we can ask, well, how much information do we gain? And here's the table that, let me just summarize it. Well, let me first summarize it within our model. Okay, so what happens if we only use information up to k 0.2, 0.3, and 0.4? All right, here's the truth, right? The truth, the answers are usually within 1 sigma of the truth, so that's good. So it's more interesting to focus on the errors, therefore. If we go only up to k 0.2, then this is the error. This is for self-fiducial volume, which is actually much larger than BOS, but it's good to know to have things tested to a much larger volume. And you see that the errors then decrease by about 30% if we go from 0.2 to 0.4. At the fixed AP, the result is the same. This one is marginalized over Alpha-Pachinski parameter, this one is not. Alpha parallel, alpha perp are also improved. These are perhaps a bit less interesting because here we don't have reconstruction, so this is not competitive against reconstruction in principle, although Alpha-Pachinski parameter, which is the ratio of these distances, is actually picks up information also from the broadband shape, and therefore can go to higher k and does become competitive against reconstructed DAO. Alright, so and then the rest of the parameters are just these nuisance parameters like satellite fractions, and various loss dispersions that are shown here. Alright, so the improvement is about 30%. So you notice this is a lot less than square root of 8, which is the number of modes at 0.4 relative to 0.2. That's the price you pay for the marginalization of many nuisance parameters. So the gain, there is a gain, but it's quite modest compared to the number of modes. There's another aspect which is to ask, well, does one need 13 parameters? Or can one get away with 5 parameters, which is what previous modelers have been using? At k 0.4, of course, with 5 parameters, you don't get even close to a good fit. So what about k 0.2? At k 0.2, they do get a good fit. You can't see by eye that there's anything wrong with it. And the price you pay by having more parameters is about 10 to 20% larger errors. So at the same k, our errors are about 10 to 20% larger compared to what the current analyses are. You can phrase this as a statement that the current errors are about 10 to 20% underestimated. All right? That's the price you pay for introducing many more nuisance parameters. Not all of them can be mapped into those 5 parameters that people use at the moment.
So for the top row, the 0.2 guy plus 1 sigma is your truth is your error bars are smaller even, right?
Sorry, what?
Am I doing that right? I mean, I add 1 sigma is 0.47, and so it's more than 1 sigma. Yeah, so their bars aren't they a little too small, or?
Well, I mean, you're worried that it's 1 sigma away?
More than 1 sigma.
Well, 1.1 sigma. No?
Yeah. So, I'm sorry.
It happens, it's in 32% of the time.
Right, okay.
Yeah. So anyway, so that's the bottom line, right? So I think this is good. I think the current, in principle, this could have been a lot worse, right? So 10 to 20% underestimate of the errors is not so bad. What is perhaps more disappointing is that k 0.4 we don't actually seem to gain all that much more.
But in the last row, don't you bias your estimate if you go to lower k max from 4.2 to 3.4? Looks like 2 sigma difference. Well, there's no true value.
Yeah, there's no true value. I don't know what the true value. Maybe it's in between these two. I don't know. This one is not that small either. Now, say the true value is 3.7, then it would be 1 sigma away from each one of them. I don't know what the true value is.
Is the following exercise at all useful, that you see how much you can get from the regime where you have some non-trivial random correction? You know, like suppose you compare the Kmax equals 0.2 result with Kmin point, I don't know what the right number is, 0.1, 0.4. So like you know, you get...
Yeah, but you're not breaking the degeneracy sufficiently then anymore.
No, it's just a consistency check on the non-linear.
Oh, you mean that? But I suspect that if you just use 0.2 to 0.4 degeneracy, you do need the K less than 0.2 to break the degeneracies. Yes.
Try introducing more parameters so that the residual error is, just equally small at high K.
So which residual error? Sorry.
No, like the 1 to 2% at 0.4. Are you talking about as a residual error? I'm just curious if you try to introduce more parameters to marginalize.
Sorry, which residual error? This?
This one, yeah.
But there's nothing. I mean, this is consistent with noise, right? It's consistent with fluctuations in the simulation. There's no systematic trend here.
So you're saying that's the best you can do?
Well, I mean, by eye, I would say yes. I mean, I don't see any need to introduce more parameters, because it's just standard fluctuation around noise simulation. This is average over 10 simulations and stuff like that. There's still some fluctuations. Okay, so all right, let's move on. The next question is how do we deal with systematics? So I won't talk about all of possible systematics, but there's one specific. There are two types of systematics that we have addressed. One is just DESI. This is very specific to DESI, but DESI has these 5 passes, but they're very non-uniform. How many visits each patch of the sky will have. Sometimes, here's what we call coverage. Sometimes, some areas will only be visited 2 or 3 times. On average, most of them are 5 times, but then there's also some areas that are visited 9 times. Now, because of this, then you pick up more galaxies in certain directions than in other directions, especially the ELGs. And here's the pattern, of the randoms. And you see the pattern has imprinted large-scale structure in it. In fact, it turns out to be very close to the BA scale. This quasi-periodicity that you see here. Now, there are 2 things. There are 2 ways to handle this, and I'll describe both of them. So I'll start first with how to handle this with randoms, and second, I'll talk about the transverse effects, which are more general. Okay, so randoms, what are randoms? Randoms is a way to compute the mean density, okay? So this is basically this thing, right? So if you compute the mean density per each patch where you know how many visits you have, which you can do, then there's one thing that we need to always normalize the randoms to, which we always need to normalize them to the observed number of galaxies, okay? So, because we want that the mean, we want to talk about the overdensities. Okay, overdensity is, let's see if I have this. No, I don't have it. Overdensity is number of galaxies minus the mean number of galaxies. This average has to be 0. Well, it can be 0 not over the whole survey, but over just the different parts of the survey. So imagine you have different parts of the survey which have different depths. Then you need to pretty much, let's say you have two patches of the survey. One is deeper than the other. You want to normalize randoms separately for this patch versus this patch. Okay. Here, what we are proposing is we want to do this, but for each individual different coverage number. Okay. So if you have 9 here and you have 5 here, then you want to put together all of the patches with 9 and all the and normalize them separately from all the patches with 5. Okay. So if one does that, then let me just show you the results. So first of all, here's the result if you don't do anything. These are now wedges, power spectrum wedges. If you don't do anything, the fluctuations are very large, because as I've shown you, that there's a very large scale modulation there. On the other hand, if you do this this normalization of the randoms, then this is the blue line, then the effects become much smaller. There still is something. Especially for the first move-in. I'll describe how to handle this later. But what we see is only a few % effect, and therefore, in principle, this is something that simulations can handle, as opposed to, for example, I'm only going to show what is going on here. You can see here it can be ordered, order of magnitude here at very low k. Okay. So, but let me move on now to the more interesting question is, well, what about if we have okay, so let me just summarize this. This we can handle with simulations, I think. But there's a more general question, which is there are all sorts of angular structure imprinted on the large-scale structure. For example, we can have variable PSF, we can have variable star galaxy separation, we can have ducks, extinction, pretty much most of the things we can think of really are angular, like completely angular, have nothing to do with the redshift. So the question is, can we remove these? And I'll describe here a procedure when we can remove them if they are additive. Okay. So the basic idea is, well, if they are angular, means they don't have, in the power spectrum, they are all transfers. We call this mu equals 0 bin. So mu is the angle between the k parallel and k perpendicular. So these are all k perpendicular terms. And so, if we can isolate this term, we can eliminate it. The problem is that at the current level, the procedure, how we measure the power spectrum is goes to this so-called Yamamoto estimator. Yamamoto estimator counts pairs and does a Fourier transform on them, but it can only handle multiple moments. Okay, so we can only fast evaluate multiple moments, not directly the wedges in the power spectrum. Because of that, when we can rotate now these multiple moments into these wedges, but these are more like pseudo wedges. They're not exactly sharp mu bins. They're more having transformed from multiple moments. The higher multiple moments we go to, the better we can do this. Okay, so that therefore suggests that if we want to get rid of this systematic, it actually pays to go to very high multiple moments. Even though cosmology information, which I haven't emphasized so much before, but there was this problem here. I mentioned to you that these errors go up very rapidly. Most information is in monopole and quadrupole. Even hexadecapole has a lot less information. And then beyond that, there's even no information at the linear level. We have run, I should mention this, we have run this analysis by adding L equals 6 and 8, and it changed nothing. So no cosmologic parameters changed. So adding higher multiple moments doesn't really help with cosmological information. But here what I'm talking about is something else. I'm talking about can it help for the systematics. If the systematics are completely angular transfers, you want to go to high L, rotate them into these pseudo wedges, and then try to remove the mu equals 0 bit. Okay, so that's the idea. Well, it turns out that when you have finite number of multiple moments, you cannot do this. There's always some contribution from a higher. There's always some contribution from mu equals 0 to this wedge. But there's something else we can do, which is here I'm showing an example. For example, when we do this rotation. And this is contribution from mu equals 0. Okay, so this is an expression here, taken from this paper here. And you can see that you can choose non-uniform mu wedges such that this mu equals 0 term vanishes. Okay, you can do this for all the wedges except for the first one. All right, so that's the idea that we choose non-uniform wedges such that the transverse term completely vanishes except in one of them. So if we only went to L max of 4, we would pretty much throw away 1/3 of data. So that's not good. If we go here, I'm showing you an example for L max 16. These are these non-uniform wedges. And you can see basically the idea is, these multiple moments oscillate as L max plus 1. And so, they have just about right number of zeros so that we can always choose enough zeros for all of them except for the first one. So in this case, we have 9 of them. We throw away the first one. We're left with 8. There's one more technical aspect that has been introduced in this paper compared to the previous one. We use spherical harmonics decomposition instead of Cartesian decomposition. So our number of FFTs scales as 2L plus 1 instead of L squared. All right. So at high L, this is actually quite a big deal. For example, at L16, we need 153 FFTs instead of 525.
So, Uros, I think the paper that introduced this idea was actually the one I wrote with Daniel a year ago for the 2.0.
Okay, good.
Years
Yes.
ago. Like,
Here it was first time implemented, right?
No, we implemented it also. We just never made that public.
Okay.
But this was the first time for the power spectrum we did it through the 2.0.
Okay, good. By the way, you cannot do this with a correlation function. You have to do this with a power spectrum. This transfers, isolating transfers to the mu to 0 only works in the power spectrum. Okay, good. So if you ask how much information do you lose, let's focus on f sigma 8, which is shown here. If you have L equal 4, then you're losing quite a lot, 50% error, because you've thrown 1/3 of the data away. If you go to 16, then you lose 8%. And you need to see how this number then goes down with the error. So, you know, at L equal 16, therefore, you increase the error by 8%, but you have, in principle, gotten rid of a lot of systematics. So, this is, I think, a useful way of moving forward. There's another advantage of this procedure, which is the covariance matrix. Here I'm showing the covariance matrix for these uniform wedges, where you don't get rid of this thing, and you see that they're quite strongly correlated. Right? Even though these are pseudo wedges, right? There's a lot of correlations between them if they're non-uniform. And moreover, actually, the covariance matrix is actually singular. It turns out to have a very large dimension number. On the other hand, if you go to these non-uniform wedges, then it becomes quite diagonal. This is for a periodic case. This is for more realistic boss case with a window, and you see, you know, there's some more spread of diagonal due to the window function, but it's not too bad. It's still quite diagonal. Okay, so we do still need to work on the window issues here, but in general, this is a useful way to think about computing the covariance matrix, because the covariance matrix is near diagonal, and the diagonal power we know in a power spectrum, in a wedge power spectrum, is just given by 2p squared divided by the number of modes, where p is the actual power at that wedge. So in that sense, this is a useful way to extract, write down analytic covariance matrix. Okay, so in the remaining time, I want to talk about the non-Gaussian part of the covariance matrix. So you may have heard that some people think covariance matrix is a huge challenge. They are running tens of thousands of simulations. They think this is a very hard problem. However, as I just said, the disconnected part, the Gaussian part of the covariance matrix is very easy. This is basically just this, right? Or this. So okay, there's some window function effect which we still need to put in, but otherwise it's just this 2p squared divided by number of modes. So the remaining part is therefore the connected part, which comes in two components. One is it's all trispectrum, but the trispectrum is split into two parts. Okay, the trispectrum there's a trispectrum component from the modes outside the larger than the scale of the survey. We call these either beat coupling or supersample covariance. And this has two effects. One is the dilation effect, where you're changing the scales by 1/3 of the fluctuation on the size of the survey. And then the second effect is because we're changing curvature on the scale of the survey, second effect has to do with the amplification of the modes, either up or down. The simplest way to think about this is modes grow faster if you are in a locally overdense, in a closed universe, and they grow slower if you're in an open universe. Okay, so you're changing the curvature, and that's what this effect here is. Right now I'm talking only about dark matter. I'll come to the galaxies later. Okay, so that's from the modes outside the survey, so the so-called supersample variance. The modes inside the survey, so these are basically the modes that average to 0. There we have to do the trispectrum analysis. So we've done this for the dark matter. The tree level has already been done by Skochimara et al. So this domain is very low K, but otherwise this term is not very important. Then the one loop contribution to the trispectrum, you can think of it as basically as the following way. You can ask Well, what happens? What's the response to a long-variant mode, but one is still inside the survey? You know, so this at the first order, the response will be 0. The second order, it won't be 0, right? Because you have positive and negative term. Think of it as something that is periodic in a box, goes up and goes down. At the lowest level, the positive response and negative response cancel out. At the quadratic level, they don't. Right? So that's the way to think about it. Now you ask, well, what is the covariance of this? It has to do with the fact that these modes are random, they're stochastic. So you do sampling variance calculation of these long-variant modes. You multiply with the response of the small scale modes to the long-variant mode, and that's how you build up the answer. Okay, so that's what we have done in this paper. By Irshad Mohammed et al. I won't go into details, but here's, for example, how we can write this response in perturbation theory. It's we can write it in terms of the function derivative, and with some f2 square and f3 and so on. So let me show you. So here's the response basically when you do this low k limit, and one way to think about it again, it's something proportional to the power spectrum. Then there's something proportional to the first derivative. This is this dilation effect, but in this case, there's also something. Okay, so here's the function of so I'll skip that. And then, as I said, then you just ask, well, what is the sampling variance of the low k modes, which are responsible for this? The lower the k, the fewer the modes. Okay, so that's why it's p squared as the number of modes. So even though there's more power at high k, at low k there's fewer modes, so the two kind of cancel out. Well, they don't really cancel out, but this expression here peaks. In fact, I think we have a plot. This is the expression. It kind of sort of peters out at k of 0.1 or 0.2. There is some contribution from higher k. The higher k in the non-regime we know have to be suppressed. We know that there is no response. Think about it, for example. I don't know, you're in a virialized region. The modes don't even get to do anything. So there's a way to handle this. Which I won't go into detail, but most of this comes, you can see, from the modes between 10 to the minus 2 and 10 to the minus 1. Okay, so these are large-scale modes, and we're looking at basically the response of the small-scale modes to these large-scale modes. And that's a one level. Okay, so the bottom line is, we do pretty good. This is when you add up all these terms, we do, this is the diagonal term, the disconnected part, and here are the off-diagonal terms. This basically at a given k prime, we're scanning k. So let's say k prime 0.21, you see we're getting quite a good total expression for the total. Again, this is 3-level term that dominates a very low k on the diagonal terms. For example, this is a one-loop term that dominates a high k. And again, as we go to higher and higher k, then the diagonal term actually is no longer that important, no longer that much bigger than the off-diagonal terms. So that is a signature of the non-Gaussian covariance matrix. Okay, so you can ask, what do we do with this? Well, one way, and this is the same as version 1, but here it works even better. Okay, so it's really, really quite good. But this is all for dark matter. Alright, so you can ask, well, what do we do with it? Well, one way, of course, is to plug in this full covariance, analytic covariance matrix into the machinery. So instead, we have looked at something else. Sorry. I should mention, this is for periodic simulations. Alright. And then, if you don't have periodic simulation, then you also have to add this other term, supersample term. Which is, significantly larger actually, but not completely dominating. And here are, for example, the final results for that thing. Again, pretty good agreement between the total, which is green, and the simulation, which is red. So what do we do with it? Well, one thing to do is we can try to look at the eigenvalue structure of this covariance matrix. And it turns out that it's completely dominated by a single eigenvalue. So that means you can write this covariance matrix as some, single eigenvalue, I guess, or some variance, and then a single eigenvector. Outer product of the eigenvector, and this eigenvector looks like this. You see, if you well, actually, this I should say this is C. This eigenvector divided by the power. Okay, it's kind of flat. All right, so this is sort of like just an amplitude up and down, not completely because there is some structure. But in the first approximation, you can think of it as just changing a bit up and down. Okay, so given this, then what one can do is one can simply add this eigenvector to the analysis as an external parameter, and then that's one way how to handle the covariance matrix. Right? You just add another parameter, and you treat the rest as being Gaussian. Here, for example, we looked at PDF of this thing and so on. So yeah, thank you. Okay, so let me skip this since I don't have much time. If you want to get covariance matrix from simulations, there's only one point I want to make, which is that covariance matrix is a trispectrum divided by the volume. Okay, trispectrum is an object that does not depend on the volume. Therefore, you don't need to run simulation which is as big as your survey volume. You can run a smaller simulation, extract the trispectrum, divide by the volume, and you have your covariance matrix. Right? It's the same principle as in the power spectrum. Right? The extraction of the power spectrum from a simulation has nothing to do with your data. Right? You can extract it from smaller volumes if necessary, except of course for the very low k. The low k is not a problem because that's a linear thing. So the same concept applies here. How you get covariance matrix and getting covariance matrix for a given survey does not have to mean that you have to run the whole volume on the survey. Okay, so we've tried this. This is the agreement between two different simulations. Just compare. If you compare these two lines, you see that this principle works quite well. Okay, so what about galaxies? Just last minute. We have to do the same thing, but now it gets much more complicated because we are doing galaxies in retro space. That means we have these multiple moments. But the response also, the supersample covariance response also is not just response to the mean density fluctuation on the size of the survey, but also response to the tidal fields and beyond. We can therefore decompose both the multiple moments of the data and the multiple moments of the large-scale modes in terms of their L's, in terms of their multiples. Right? So think of big L equal 2, think of this as the tidal field. Think of little l as being monopole if it's 0, quadruple if it's equal to, and so on. Right? So we have to compute all of these couplings. I mean, I'm showing them here in analytic theory. This is work done by Yin et al. And there's one more thing, is these are local. These are all relatively low to local density. Local density means we have to subtract out the bias kind of terms. And that means that this is global. But when we subtract these kind of terms, this response can be, a negative. For example, right equal to 0, it's negative actually. But that's for a specific choice of B1. In this case, it's B1 equal to. It can even be 0. So, whether this supersample covariance will be positive or negative or whatever, it's not that easy to predict because you have to account for all of these terms. In terms of comparison simulations, well, I mean, this is how it is. It's not too bad, right? This is the response. These are the responses from the simulations compared to the negative theory.
Is there some HOD you're putting in to populate the galaxies?
This is still just halos here. You're talking about simulation here, or what?
Right. The response of the galaxies to your long-range mode is presumably dependent on the HOD or so.
Well, no. I mean, this is our expression, right? This is the claim is this because it only depends on B1. This is only the supersample covariance response. Yeah, the claim is this only depends on B1.
These are 3 levels?
Sorry?
The next line is 3 levels?
Well, supersample limit, where Q over K goes to 0. So it's bispectrum. Sorry. Yeah, I mean you can think of it as a bispectrum, 3-level bispectrum in the limit of Q to 0. Okay, and finally, well, does this matter? Does non-Gaussian covariance matrix matter? Okay, so here is the ratio of non-Gaussian to the Gaussian. Bin, this depends on the binning. Okay, I don't like this kind of plots because it depends on the binning, but still, it gives you an idea. With this kind of binning, this is the this is the periodic case, so no supersample variance term. This is the non-periodic case. So you see the variance goes up a lot. There should be -1 here. So think of this as the variance of k.3 going up by a factor of 3 with this kind of binning. Is this important? Well, it's not really, because this is completely general with the bias. Bias is a free parameter. As I was telling you in our previous slide, you can choose, depending on what bias is, this can be positive or negative. And so in fact, you can adjust the change of bias so that, let's say on the multiple, there's no change. There's no obvious implication for the physics. However, when you also do the same for the quadrupole, by the way, on the quadrupole, it seems like trispectrum dominates over the supersample term. So the modes inside the survey dominate. But the effect is small, you can see, right? It's only 20%, so even a very high K. Anyway, to summarize, the supersample terms are dominant for the covariance matrix, non-Gaussian part. They look large, but they can be absorbed by the change in bias. And when we look at the change of the F sigma 8 really, we find effects, for example, for the Boss survey, we find effects which are 0.5%. All right? The error on F sigma 8 from Boss is 5%. So this non-Gaussian part is a lot smaller than any information we can extract from the data. The bottom line is, I personally think the non-Gaussian part of the covariance matrix is a red herring. It's not very important. We can just ignore it, and it will be just as good, right? So from my point of view, you can do the Gaussian part with an analytic expression of the window times, window squared times 2p squared divided by number of modes or something like that, and we're done with it. All right, no need to run tens of thousands of simulations. Okay, so here's the roadmap. Basically, I think personally that this is a good path forward using Yamamoto estimator and all of these things. There's a very interesting question: is do we need to do spherical Bessel decomposition? I personally don't see the need, but I would love to engage in this discussion because maybe we're still missing something. But we think we have something that is working and can handle most of the things we need to worry about. Anyway, so the Gaussian covariance matrix is nearly diagonal. In presence of variance, we can remove them, the mu equals 0. And finally, perturbation theory has its limitations. There is a potential that we can do better if we do go to M vectors. I think Ellen and I talked about this maybe. And so that's where there's more room for improvement.